So Pieter Kleer is an assistant professor of econometrics and operation research at Tilburg University in the Netherlands. He completed his PhD at the CWI, supervised by Jodo Schaffer, which I hope I pronounced correctly. For his dissertation, the Dutch OR Society awarded Pieter the Below Award for the best PhD thesis in the area of mathematics and operation research defended in the past 3 years. After his PhD, he was a postdoctoral researcher at the Max Planck Institute of Informatics in Germany, hosted by Kurt Melhorn. And he has joined the Tilburg University as an assistant professor recently at the start of this month. His research interests include algorithmic game theory, online approximation algorithms, and approximate uniform sampling of combinatorial objects. And today he's going to tell us about his work on the secretary problem and online matching problems with machine learning advice. This work was published in Norwich 2020. Please.
Yes, thanks a lot, Shahzad, for the introduction and for the opportunity to speak here in the seminar. So yeah, today I will be talking about secretary and online matching problems with machine learned advice. So this is sort of a problem in the area of online algorithms in the field of theoretical computer science. And we're somehow studying a variant on this problem inspired by sort of the recent search and success of machine learning. So this is a joint work with Antonios Antoniadis, Themis Gouliakis, and Pavel Kolev, who at the time were all postdocs also at the Max Planck Institute for Informatics in Germany. So before I will explain what this machine learned advice setting is and what online Vipertite matching is, I will first, as a warm-up, sort of start by explaining the secretary problem to sort of give you a feeling of what type of problems we will be looking into. So some of you might know it, but for those who don't know it, let me briefly explain it. So in the secretary problem, the setup is very simple. We have a set of secretaries or elements that arrive over time. And usually the assumption is being made that they arrive in a uniform random order. So we have n secretaries, we have some kind of permutation of these secretaries, and one by one they arrive at our office, if you will. And whenever a secretary arrives, he or she reviews a value VI that they have. And the goal for us is to decide irrevocably whether we want to select or reject the secretary. And the constraint is that we are only allowed to select one secretary, and the goal of the problem is to select the secretary with the maximum value V star, which is just the max of the values VI. Now, just as an illustration, so basically what we have to do is the secretaries arrive one by one. So these are on the horizontal axis, we have the time step. So the secretaries start arriving, they all have a value. And whenever a secretary arrives, we have to decide, do we want to hire it or not? So for example, at this point, we might see this secretary, and we might say, okay, well, the value looks like decent, so we're gonna accept this secretary who has this value too. Now, afterwards, more secretaries might arrive. They can either have a lower value, but they might also have a higher value, but we can no longer select them because we have already selected the secretary. And some other goal of this problem is to actually somehow come up with a clever way of selecting a secretary that either has the best possible value or a value which is in some sense close to the best possible value. So in this case, this would be the best secretary overall, I hope, because the other one is lower again. So we've selected this one, but we could have selected that one. And again, sort of the goal is to select a secretary whose value is somewhat, in some sense, close to the optimal value. And more general, you can study in this context so-called online selection problems. So here the setting is similar. So you again have a set of elements, E1 up through En, that arrive in some kind of uniform random arrival order. So again, every arrival order of the elements is equally likely. This is essentially a random variable. And still every element EI has some kind of value VI, which is reviewed whenever an element arrives. And again, we have to decide upon arrival of an element whether we want to select or reject it. And this decision is irrevocable. Now, the only difference with the general setting is that instead of only selecting one element, so one secretary, we are actually allowed to select multiple secretaries. And usually this is subject to some kind of combinatorial constraint. So not every possible combination of secretaries or elements is allowed, but only certain subsets are allowed. So one other case that you might think of that I will also illustrate later is that of online bipartite matching, where in some sense the edges of a bipartite graph arrive online, and we are allowed to select a subset of edges that together form a matching in the graph. But we will see this later on. But this is sort of the high level goal in case you are allowed to select more than one element. Now, in general, finding the best possible set S, so the set that actually maximizes the sum of these values, that's usually a very difficult problem if you want to do this in an online setting. So you can already think of the secretary problem. If you, for every possible arrival order, would want to somehow come up with a way of selecting the best possible secretary every time, you can actually prove that this is not possible. This is a very, you might say this is impossible to guarantee. So in general, what we will be interested in are so-called approximation algorithms. So that's something that's very common in the area of online algorithms and theoretical computer science, where you say, okay, I'm happy if I can pick up a set S bar. So there's two sets here, S bar and S star. And S bar is the set which is selected by your online algorithm. So that somehow decides which elements to select, which elements to choose and which not. And S star here is the so-called offline optimum, which is of the best you could achieve if I would give you all the values VI upfront. So if I just give you all the values, you can figure out in a smart way, okay, which combination of items that is feasible that I am allowed to select together give me the best possible value. And what is now an alpha approximation? Well, that's an algorithm that with the expectation taken over this uniform arrival order selects a set whose value is at most or is at least a fraction alpha of the optimal set. So one way to think of this is that say that alpha is a half, then essentially what this inequality says is that the value of the set S bar that I select in expectation is at least half the value of the optimal set that I could have picked. And this is what we call an alpha approximation. And in general, what we are interested in is finding constant competitive or constant factor approximation algorithms for these online selection problems. So again, as these some examples, so we have seen the secretary problem before. There's also this online bipartite matching that I already mentioned earlier, and that will be that I will talk about later on as well. But you might also think of something as the matroid secretary problem for those who know what that is. So in that case, you're allowed to select multiple elements under the subset or under the constraint that the combination of elements that you have selected should be a so-called independent set in your matroids. If you don't know what matroids are, that's not a problem. We won't talk about them any further in this talk, but just to give you some examples of what online selection problems look like. Okay, now the second thing in the title that I have not yet explained is this notion of machine learned advice. So this is basically a variation on the classical setting of online selection problems, where which is inspired by the success of machine learning. And the high level idea in this setting is that somehow you have some kind of machine learning oracle that somehow predicts an aspect of your problem that you have not seen so far. So this could either be a prediction about the input that has not yet arrived, or, for example, about your offline optimal solution. So in the example of the secretary problem, it might be that based on sort of previous iterations of this problem, you might have collected some historical data about what typical values, say, of the best secretary, what a typical value of the best secretary is. And based on this data, you have some kind of machine learning oracle, some kind of machine learning algorithm that has come up with a clever prediction of what the best, of what the value, for example, of the best secretary is. And our goal is now to include this machine learned advice in an alpha approximation for, in this case, the classical secretary problem. But there is, of course, a problem, and it is that machine learning algorithms are not always as good as we want them to be. So in general, machine learning algorithms perform very well on various tasks and are able to sort of generate useful, in our setting, useful predictions. But in general, the machine learning algorithm might also be wrong. And that's something we also want to take into account in our setting. So we have this theoretical guarantee that something is an alpha approximation, but somehow if we start to include this machine learning machine learned prediction, we still want to make sure that we don't sort of screw up our approximation algorithm if it turns out that the machine learning prediction is bad. So that's sort of the high level thing that we take into account, which is the quality of a prediction. So you predict a part of your solution or your input that has not yet arrived, and you somehow want to start including this in an alpha approximation. So we will do this later on for the secretary problem as well. And one important parameter that we will need is the quality of your prediction. And the quality of this prediction is measured in terms of the prediction error, which we throughout this talk call eta. So again, I will illustrate this later for the secretary problem, how this works. Now, again, just once more, what is the goal? So the goal is to include this prediction in an existing alpha approximation such that the following conditions are satisfied. So the first thing, what we want is we want to get an improved approximation guarantee if the prediction error is small. So if the machine learning oracle told us something about our problem, for example, in the case of the secretary problem, told us predict the value of the best secretary, which was very accurate, then somehow we wanted our algorithm also outputs a secretary whose value is very close to the best possible secretary. But on the other hand, we also want to make sure that if it turns out that the prediction is very bad, so if the prediction error is very large, then we don't sort of want to lose our full approximation guarantee alpha. So it might be that we had a half approximation before, but we want to avoid the situation where if the prediction actually turns out to be bad, that we are all of a sudden can give no theoretical guarantee anymore about the approximation guarantee. So one other way to look at this a bit more in words is that we want to get, say, a best of both worlds scenario. So we want to get an improved approximation guarantee in case the machine learning oracle is accurate. But on the other hand, we also still want to guarantee that we have some kind of approximation guarantee in the worst case when the oracle is inaccurate. Yeah, the best way to think about this in terms of pictures is the following. So essentially what we do is we introduce the prediction error eta as sort of a variable in our performance guarantee. And so one thing to think about this is, say that alpha, again, if we take this example of alpha as a half, then what this picture illustrates is that, okay, well, you need to come up with a new algorithm that includes your prediction in such a way that if your prediction error is small, that you actually get a better approximation guarantee, so something that's closer to 1. It doesn't necessarily have to be 1, but it should at least be better than alpha. But in the worst case, you say, okay, if the prediction error turns out to be very large, then still eventually we want to have some kind of constant factor approximation guarantee. So this could, for example, be alpha is 1/3. So, oh, sorry, not alpha, but just the new worst case approximation guarantee might drop to 1/3. So that's the general scheme that we are aiming for here. So you have some kind of known alpha approximation. You want to include the prediction in such a way that if the prediction error is small, that you can sort of theoretically give a better approximation guarantee. But on the other hand, if the prediction error grows large, then you should still have some kind of constant factor approximation guarantee.
Can I ask a question here?
Yes, sure.
So this error that you are, I think Okay, this error that you're talking about is like with high probability. So it's you have a prediction for the value of vi that your secretary gives you, right? So
Yes.
deviation from that value with high probability, like how do you define the error?
So I mean, the error is essentially it's an unknown parameter.
Yeah.
But we want to include it in the analysis. So we assume that it's for
the maximum deviation from the actual value.
Yeah, exactly. Yeah, this is what I will introduce later on as well. So indeed the prediction for the set what the prediction error for the secretary problem will be is if you get some kind of prediction P, then the prediction error will be defined sort of as the say here just the difference between say the prediction and the actual true optimum in our instance. But it is essentially a deterministic concept.
Okay. Yeah, thank you.
But so it is true, like in practice, usually you don't know the prediction error, but we want to say something about what happens to the performance guarantee of our algorithm when you would know the prediction error.
Because what confuses me is that usually when you talk about alpha approximation algorithm, it's defined as deviation from like the optimal with high probability, but you are just looking at the expected value right now for your
yeah. So we only look at sort of the only randomness here is that comes from the random arrival order of the secretaries.
Mm-hmm. Okay, thank you.
Okay, so somehow my Zoom bar, there is. So so we are definitely not the first ones to introduce these type of problems. So there is a very large literature that sort of grew since a couple of years ago, and where people study this type of paradigm in various different problems. So for example, in the ski rental problem, in online scheduling problems, caching, metric algorithms. And also recently there was actually another paper where they did some kind of version of the secretary problem with prediction. So if you would be interested in this, I would also recommend having a look at this paper. So yeah, just as a side note, I'm not going to explain all these problems in detail, but there has been sort of a growing literature, both in the theoretical computer science community as well as the machine learning community, where people study problems, online problems, with the inclusion of some kind of machine learned advice. So it's definitely a growing area since the last couple of years. Yeah, so let me get back to the secretary problem and explain to you a bit more formal how we. So I've already explained actually what the prediction is that we consider, but also I will explain how we adjust sort of the classical algorithm for the secretary problem to include the prediction. But let me first briefly recap the secretary problem. So again, we have these elements that arrive over time, uniform random arrival order. Value vi is reviewed upon the arrival. And the goal is to select the maximum secretary, or the secretary with maximum value. Now, this problem has already been studied a long time ago, in the 60s actually, and there's an algorithm for it, which also turns out to be an optimal online approximation algorithm, which was discovered both by Lindley and Dinkin in the 60s independently. And the way in which this algorithm proceeds is very simple. I will also illustrate it on the next slide with an example, but it basically consists of two phases. So in the first phase, which is sometimes called an observation phase, you essentially do nothing. So there's a bunch of secretaries arriving. You observe their value, but you do not select any of them. And then you enter the second phase. And in the second phase, what you do is first you set a threshold, which is the value of the best secretary you've seen in the first phase. And what you do then is you say, you let the remaining secretaries arrive, and you select the first secretary whose value exceeds the threshold. So it's a very simple algorithm. You observe a fraction of n over e of the secretaries, or you set a threshold, which is the best you've seen in the first phase, and then you select secretary that arrives after that, who's the first secretary whose value exceeds the value of this threshold. And it turns out that this is an 1/e approximation for this problem of, it's sort of a 1/e approximation for the maximum value V star. So again, what it says is that if V bar is the element that we select, then with the expectation taken over the uniform random arrival order, the expected value of this element that we select is at least 1/e times the value V star, which is this offline optimum. So that's sort of the maximum you could have gotten if you would have been able to see all the values up front before they arrive online. And yeah, so just let me illustrate it also with an example. So we have this phase 1 and phase 2. So secretaries start to arrive. And at the end of phase 1, what we do is we say, okay, what's the best secretary we've seen so far? Well, it's this one at this value T. And now in phase 2, sort of more secretaries start to arrive, and we select the first one that exceeds the thresholds. And again, the claim is that if you do this, then in expectation over the random arrival order, you select the secretary whose value is at least 1/e times the best possible value. Okay, so now what we do in the papers, we sort of include a prediction for this optimal value V star. So I already mentioned it before actually, but I'll go over it again. So what we do is we include a prediction P star for this optimal value. And as a prediction error, we take this difference. So I should say maybe already at this point is like, this is a very simple problem. And this is sort of in our paper, this is more of a toy model. What we also do in the paper is we study more involved online selection problems, but I've chosen to illustrate all the concepts with the secretary problem because that's most easiest to explain and to convey also the intuition of what's going on. So having said that, so this is the prediction error that we define for the secretary problem, where again, P star is a prediction for the optimal value. And now, again, in terms of what I've already explained before, the goal is to design an algorithm, and we actually focus on deterministic algorithms such that the following holds. So what we want is, we want that when the prediction error eta is small, we should get an approximation guarantee that's better than 1/e. So remember, 1/e was this approximation factor that the algorithm of Lindley and Dinkin gives you. But at the same time, we also want to guarantee that if the prediction error is large, so if the prediction is way off, then we want to get an approximation guarantee, which is approximately 1/c times e, where c is some constant greater than 1. So we allow a deterioration in the approximation factor, but at most by a constant factor c. So again, in terms of a picture, what it looks like is as follows. We have this 1/e approximation from Lindley and Dinkin. And the goal is now to somehow include the prediction P star in our secretary algorithm in such a way that when the prediction error is small, so when the prediction P star is very accurate, then we should get a performance guarantee that's better than 1/e. But when the prediction error becomes large, the approximation guarantee is allowed to sort of get a bit worse, but only up to a factor 1/c times e for some constant c. Right, so that's again the high level thing that we want to achieve. So in order to explain how we incorporate this prediction in this secretary algorithm, this two-phase secretary algorithm, the first thing you might wonder is what would you do when the prediction is good? So suppose that the value that your machine learning oracle predicts is actually very close to the offline optimum V star. How would you proceed in your algorithm? Well, sort of in the secretary problem, again, this is the simple problem. The most obvious thing to do is, well, you're just going to wait somehow for a value. You're going to wait for a secretary whose value is close to the prediction V star. So you said the best secretary might have a value of 500. So what you're just going to do is you're going to wait until you get a secretary whose value is approximately close to 500. That's sort of the obvious thing to do when the prediction error is small. So in order to do this in the algorithm, we need sort of a small adjustments. And what we do for technical reasons is we lower the predicted value by lambda a little bit. So we want to incorporate the situation where you might have like a prediction P star, but the value of the best secretary might be slightly lower than P star. So in order to make sure that we don't that we still select the secretary if its weight is very close to the prediction but slightly lower. We sort of lower the prediction p star by a value lambda. Also, one way to think of lambda is actually as some kind of estimator of the prediction error eta. I'm not going to go into this here, but that's one other way to think of it. So that's what we do. So we have this predicted value p star. We say we lower it a little bit by lambda, and now we're just going to select the first secretary whose weight exceeds this threshold value of p star minus lambda. So again, the secretaries start to arrive, and this is the first secretary who exceeds this threshold. So this will be the one that we select, and then afterwards some more secretaries might arrive. Now, there are, of course, a bunch of issues with this algorithm, namely that it's way off if the prediction error is large. So on the one hand, it might be that the prediction error, if the prediction error is large, it could be that the predicted value that we get is way too high. So if we only select the first secretary whose weight exceeds p star minus lambda, then of course, in this case, we would not select anything because all the values of the secretaries are actually much lower. And on the other hand, we might also have the problem that if the prediction is way too low, then we might select a secretary very early on whose weight is also way too low. So either we select nothing if the predicted value is way too high, or we select something with a very low value if the prediction would be very small. So this very simple algorithm, it works well if the prediction is close to the optimal value, but if it's too high or too low, this does not give you anything. And in particular, the approximation guarantee of such an algorithm could become arbitrarily bad. So what we do then instead is we still use this sort of algorithmic idea of what you do when a prediction is good, and we incorporate this in the classical secretary algorithm of Lindley and Dinkin, with this additional guarantee that we have this fail-safe of that when the prediction is bad, that we still get some kind of meaningful approximation guarantee. And the way we do this is as follows. So instead of considering a two-phase algorithm, we will actually be considering a three-phase algorithm where gamma and delta will be parameters that specify the lengths of the phases. And again, there is this parameter lambda that we use to slightly lower the prediction p star that we have gotten. Now, our algorithm then simply looks as follows. We again have this observation phase. So what we do first is for the first gamma n secretaries is we select nothing. So we just let them arrive, we observe their values, but we don't do anything. Then we move to the second phase where we try to exploit the predictions in a similar fashion as we did on the previous slide. So the idea now is to again set a threshold, but this time we set a threshold which is the maximum of, on the one hand, this p star minus lambda, so the slightly lower prediction. But we also have a second term in the max, which is the best element that we have seen so far in the first phase. So in the inclusion of this part actually guarantees that if the prediction would be too low, that we avoid choosing something which is, that we avoid selecting a secretary whose value is too low compared to the optimal value. So this is sort of what we do then in phase two. We say, okay, we set this threshold t, and between secretary, the fraction gamma n and the fraction delta n, what we do is we select the first secretary whose value exceeds the threshold. So again, this is in a similar fashion as what the classical secretary algorithm does. But then there's also a phase three where we fall back to the classical algorithm. So it might happen that, again, if the prediction is way too high, that we don't select anything in the second phase. So in order to make sure that we still get some kind of constant factor approximation guarantee, we have this third phase as a sort of a fail-safe where we fall back to the classical secretary algorithm. So what we do here is we reset the threshold. So we forget about the second, the threshold that we had in the second phase, and we set a new threshold, which is now the best value we have seen in the first two phases combined. And then again, we have this simple threshold policy that says select the first secretary whose value exceeds the value of the threshold. So let me illustrate this algorithm also with an example. So again, we start out with having this prediction p star that we slightly lower by lambda, and now secretaries start to arrive over time. it could be that, okay, in this first phase, in this case, only 3 secretaries arrive. Then we have this, again, we have this maximum value of the weight of the secretary, that's the maximum value of any secretary that arrived in the first phase. And now for the second phase, we set this threshold, which is the maximum of these 2 values. So in this case, it would be P star minus lambda. And then more secretaries arrive in the second phase, and we select one if it exceeds the maximum of these 2 values. So in this case, we select this secretary. And then some more secretaries might arrive in the third phase. Now, again, what happens is, so in this case, we would have selected this secretary, but again, to explain the intuition from the previous slide, on the one hand, what happens is, okay, so if the prediction is close to the optimal solution, then in general, we will select an element whose weight is close to the optimal value. But the problem, again, can be that P star minus lambda is way too low compared to the maximum value, in which case we would select something with a value that's too small. But we try to avoid this issue by defining this threshold in the second phase as the maximum of these 2 values. So that's sort of the point. Like if this would be way too low, then this threshold, value kicks in, and this one guarantees that we will still, if we select an element in the second phase, and an expectation, it will still be an element whose weight is close to the optimal value. And on the other hand, if the prediction would be too high, then what happens is that we might not select anything in phase 2, but then in phase 3, we fall back to this policy where we set a threshold to be the best that we have seen in the first 2 phases combined. And then in this case, for example, we would still select some elements from the third phase. So that's how this algorithm works. We have one phase where we try to exploit the value of the prediction that we got, but we also have this phase 3 essentially that has to take care of the fact that, okay, if the prediction was very bad, then we still want to pick up an element whose weight is only a constant factor away from the maximum possible value. So, okay, so the algorithm has a bunch of tunable parameters. So on the one hand, we have this confidence parameter lambda, and we have the length of the phases, and you can essentially play around a bit with this. So you have these 3 parameters. So depending on how you choose the length of your phases and how you set this value on lambda, you generally can achieve approximation guarantees that look something like this. Yeah, there's one funny thing going on around this value, which I will not go into too much, but it's sort of the general scheme of things that we can achieve. So depending on how you set your phases, you can come up with approximation guarantees that look like this, and there is some kind of thresholds. For example, you can actually get as close as you want to 1, but this always comes at a cost that the constant factor guarantee that you have in the worst case becomes lower. So it could also be that you have an approximation guarantee that looks something like this, but then the approximation guarantee that you get in the worst case actually becomes worse. So there is this trade-off between, on the one hand, okay, if the prediction error is very small, you can get very close to 1. But on the other hand, this also comes at a cost that when the prediction error is large, the new constant factor that you are left with, so this 1 over c times e, becomes lower. So that's something that depends on how you set the values of these tunable parameters. So this gamma, this delta, and this lambda.
So can I ask another question here?
Yes.
So these values of gamma and delta and lambda, are they like, well, in particular, is lambda and delta dependent on gamma? Because it seems like the more confidence you have on your prediction, then the phase when you are just choosing whatever is more than your prediction should be longer, and the other phase should be shorter.
Yeah, that's indeed true. Yeah. That's precisely the trade-off that you have. Yeah.
But you do you choose the value of lambda to determine the values of gamma and delta, or no? It's just like you explore different values of their interplay.
Yeah, so you can. So in for the secretary problem, we actually do, like I said, what do we do? I think we just say like it's a first So yeah, it comes from the Lambert W function. It's a bit more defined, a bit more technically on how you define the length of these phases. But this naturally actually comes up in the analysis of the classical secretary algorithm. But it is indeed true that if you would set lambda like very small, so if you have a lot of confidence in your prediction, then you would like the second phase to be very large. Because that's the phase where you're trying to exploit the prediction. So there's definitely there should be some kind of relation between lambda and gamma and delta, because it's also true if you don't take this into account, there also exist values of lambda, gamma, and delta that don't give this type of behavior. So it might be if you set them very stupidly, like indeed if you put a lot of faith in your prediction, but then you make your second phase very small, then you're really not improving.
Yeah, thank you.
Yeah, so and again, so there is this weird jump here, which comes from the fact that we choose lambda deterministically. You can smoothen this out a little bit, so you can also instead make a randomized choice for lambda. And in that case, you get a bit more of a smoother approximation guarantee. So that's sort of the difference between choosing lambda deterministically or choosing it in a randomized way. We also do this in the paper if you would be interested to see that. So yeah, just to illustrate now, what's the high-level challenge that comes up when you want to include these predictions. So in general, what we will also do for these more complicated online selection problems is that what you would like to do is you would like to have you would like to use different algorithms for different parts of the element stream. So again, all these secretaries arrived online, and we basically had these three phases. Well, the first phase is not very important, but in the second phase, we tried to exploit the prediction. In the third phase, we wanted to have some fail-safe that in case the prediction is bad, we still pick up an element whose weight is reasonably well. And that's sort of also the main challenge when you move to online selection problems where you are allowed to select more than one element. So again, as I said, what you want to do is you want to have one algorithm that tries to exploit the prediction that you get, and you have one algorithm that still gives you this worst case theoretical guarantee, which might be that again we have the 1 over E and we drop to like 1 over C times E. But the important thing is that it's still a constant factor approximation guarantee that you want to be left with. And sort of especially the high level challenge when you move to settings where there's multiple elements that you might select online is that you have to make sure that they don't conflict too much with each other, which is also what I try to illustrate for the secretary problem. So you have to make sure that you don't, like, if your prediction might be very bad and you have some phase where you try to exploit the prediction, you have to make sure that you do not make like too many stupid choices so that you cannot choose any elements anymore when you want to fall back to your fail-safe algorithm. So in other words, one way to look at this is like bad choices in one part of your algorithm or one part of the element stream should not affect the other parts of the element stream too much. And especially often this seems non-trivial to achieve, especially if you want to do this by means of deterministic algorithms. So also our focus in the paper really is on deterministic algorithms. So that's the main challenge that comes up when you want to analyze online selection problems that we do with these type of predictions. So let me now move on to the second example that I talked about earlier already as well, which is that of online bipartite matching. So in the online bipartite matching problem, what we are given is a bipartite graph. I'll give an example later on the slide as well. It's a bipartite graph where we have we have a node partition into node Z and node Y. And now the idea is that this bipartite graph has one so-called offline side and one online side. And especially we have the nodes in the online side, which will be Z for us, arrive online. And again, this will be in a uniform random arrival order. So you have this bipartite graph that we don't know, but one by one, the nodes on one side of the graph appear online. And upon arrival, what happens is that a node ZE, in this case from Z, they reviews its edge weights WE to neighbors in Y. Sorry, the E subscript should not be here. So it could be that Z is connected to various nodes on the Y side that all could have a different weight WE. And the goal is, or what we're allowed to do is we're allowed to match up ZE with a currently unmatched node on the offline side y. Or we can do nothing. So we also can decide not to match up a node. So yeah, let me just illustrate this with an example. So here we have 4 offline nodes on the y side. And what happens is that the nodes on the z side start to arrive online. So maybe z2 arrives first. It's adjacent to y1 and y2, both with value 3 in this case. And for example, we might decide to add the edge z2 y1 to our matching. And then again, another node might arrive here, z1, who is adjacent to y1, and only to y1. So in this case, we have a problem because we cannot match up z1 with y1 because it's already matched up with z2. So we need to have this, we have this feasibility constraint that the set of edges that we select together need to form a matching. And again, so here, say z4 might arrive. And for example, we could select the edge z4 y3 with this 6. And then z3 might arrive and we select the edge that matches it up with y2. And then we have selected these 3 red edges that together form a matching in the bipartite graph. And the goal of this whole problem is now to, in this online fashion, select a set of edges that together form a optimal or that form a matching in the graph whose weight is as high as possible. So this is actually in a problem that's been very well studied, especially, so this is even without the setting of having some kind of prediction or some kind of machine learned advice. So there's a long line of work on this problem. And eventually the best possible approximation factor for this algorithm was given by Kesselheim et al. In 2013, which is a 1/re approximation. And this is also best possible. So if you would give it some thought, you can show that this online bipartite matching problem is a special case of the secretary problem. Or sorry, the secretary problem is a special case of this online bipartite matching problem, in which case you would have like one offline nodes, and you have like secretaries that are all connected to this node, and they arrive in uniform random order, and you can only select one. So that's a special case. So basically what Kesselheim et al. Did is they gave a much more, they gave an algorithm for this online bipartite matching problem, which is a sort of significant generalization of the secretary problem into this domain of online bipartite matching. And as I said before, this result is also best possible. So we also study a prediction model for this online bipartite matching setting. So in this case, we now, we do not have like one prediction, but we have a prediction vector, P1 star up through Py star. So essentially what we get is we get one prediction for every of the offline nodes. And what these predictions, what these predictions say is that they predict that, again, based on historical data that they might have seen from other matching problems online, is they predict that there is some kind of offline optimal solution opt that has the property that the node y in y, so this node y on the offline side, is adjacent to an edge with weight e star y in this optimal solution. So you're essentially predicting that, okay, there is some kind of matching in the offline setting where the node y in on the offline side is adjacent to an edge whose weight is equal to P1 star or Py star in this case. And the prediction error that we now define is, again, is also a generalization of what you get in the secretary problem, is we define this as the maximum possible difference between this Py star and between the value that node y or the value of the edge that node y is adjacent to in a given offline optimal solution. So that's sort of the way to think of it. You have this bipartite matching instance, and for every node y, we give some prediction. So we get P1 star, P2 star, P3 star, and P4 star. So for example, if this would be the offline optimal matching, I'm not sure if it is, but it could be that we could have had a prediction of 1 here, a prediction of 3 here, and a prediction of like 6 here. This would be like a situation in which we would perfectly predict the offline solution. And actually, it turns out that there is a natural also a relation to another bipartite matching problem, which is already on the slide, which is called this online vertex-weighted bipartite matching. So in this online vertex-weighted bipartite matching problem, what you have is you don't have, you still have nodes that arrive online and that have neighbors to this offline side, but there's instead of the edges having weights, the nodes have weights. And in particular, if you would consider our model with perfect predictions, then the problem basically corresponds to this online vertex-weighted bipartite matching problem. So yeah, one other sort of the takeaway message of this is that in a sense, what we have is that this variant of online bipartite matching where we introduce these predictions can be seen as some kind of interpolation between online bipartite matching on the one hand and online vertex-weighted bipartite matching on the other hand. That's sort of the important takeaway from this discussion. And this was a problem that was also studied already. This was actually introduced in 2011 by Agarwal et al. So yeah, similarly as what we did for the secretary problem is we also sort of come up with an algorithm for this online bipartite matching problem in which we include these predictions. Now, I'm just going to give you a brief overview of the algorithm. It's not important that you understand all the steps, but I just want to illustrate the fact that it's similar to what we did for the secretary problem in the sense that we have these different cases. So again, in this setting, in this online bipartite matching setting, the goal is to construct an online matching M. Now, again, the algorithm consists of 3 phases. So first, we have an observation phase where we let a bunch of nodes in Z arrive online, but we don't do anything. So we don't select any of the edges that are adjacent to those nodes that appear in the first phase. And then what we do in the second phase is actually something similar to what Kesselheim et al. Did to give their one-over-read approximation, which basically works as follows. So it's not important if you don't get this step, but let me briefly sketch it for those interested. So what this algorithm of Kesselheim et al. Does is it computes an offline optimal solution on the graph you have seen so far. So maybe the nodes 1 up through I have arrived. Oh, sorry, this should have been a Y instead of an R. You compute an offline optimal solution on the part of the graph that you've seen so far. And if the current node, so if the node that has currently arrived, so the node in step I, if it is currently unmatched, or sorry, if the offline node that it gets matched to in this offline optimum is currently unmatched, then you add the edge to the matching. So again, you compute an offline optimal matching. You have this node I that just arrived. It might be matched up with some node R on the offline side, which is Y again, sorry for that. And you say, okay, if R on the other side, on the offline side is currently unmatched, then you add this edge I of R. So that's what you do in the second phase. And then in the third phase, we try to exploit the prediction. So the second phase actually tries to make sure that we, at least in case the prediction is bad, we sort of pick up a bunch of edges whose weight together at least form some kind of constant fraction of the offline optimal solution. And then what we do in phase 3 is we try to exploit the prediction. So one thing to observe is that we do it actually the other way around for this problem. So in the secretary problem, we first try to exploit the prediction and then at some kind of fail-safe algorithm, but now we do it the other way around. And the reason for that is that if we want to analyze our algorithm, it's better if the Kesselheim et al. Algorithm comes first. This is mainly for technical reasons why we do it in this order. But okay, this was phase 2, and what you do in phase 3 is we try to exploit predictions, and this we do by means of running some kind of greedy algorithm for this vertex-weighted bipartite matching problem. On a high level, it's not important to know exactly what this is, but it's very simple. You just put all these predictions P star minus lambda on the nodes. And what you're just going to do is there's some other nodes that arrive online, and you're just going to greedily select edges in the graph. So a node arrives, you just look at, okay, what's the best possible offline node I could match it up to, and you select that edge. So again, this also illustrates a bit this interpolation between, on the one hand, this online bipartite matching problem, and on the other hand, this online vertex-weighted bipartite matching problem. But the main thing to see here is that the algorithm is of a similar flavor as the secretary problem with predictions, but things become much more involved because now we are allowed to select multiple elements instead of just one. And again, sort of there are some tunable parameters in this algorithm. So we have this lambda, we have gamma and delta that determine the sizes of our faces. And you can get sort of conceptually similar approximation guarantees as we saw for the secretary problems. Again, in terms of this prediction error eta. It should note actually, we should note that in this setting, the best one can hope for is a half approximation. So in the secretary problem, we had this property that we can choose the parameters in such a way that if the prediction error is small, we can, in a sense, get arbitrarily close to a 1 approximation. But for this prediction model in the online Vipertite setting case, this is not true. And this follows from the fact, again, from this relation to online vertex-weighted Vipertite matching, for which the best you can hope for is a factor of a half if you consider deterministic algorithms. So it's also not guaranteed that if you introduce a prediction model that you can always get arbitrarily close to a 1 approximation in case the predictions are good. So this really depends on how you define your prediction model. So as a summary, what we do is we include machine learning predictions in existing alpha approximations for online selection problems with the property that we get an improved approximation guarantee if the prediction error is small. But on the other hand, we don't want to lose too much in our approximation guarantee when the prediction error is large. And this is sort of the main picture to keep in mind and as a takeaway of what we try to achieve for our online selection problems. And so we've studied these two problems. So we studied this classical secretary problem in our paper and this online Vipertite matching problem that I illustrated before. And we also consider one more problem, which is the graphic matroids secretary problem. Let me say this in one line what this is. So in the graphic matrix secretary problem, this is also an online selection problem. So what you have here is you have a graph G, whose edges now arrive online in a uniform random order. And the goal is to, all these edges have a weight, and the goal is to select a spanning tree of your graph of maximum weight. So what happens here is that the edges arrive online one by one, and for every edge you have to decide, do I want to include it in my tree, yes or no? And the only thing is you have to be aware of the fact that you cannot select edges that create a cycle in the graph, because that would violate the constraint of being a tree. It's not important if you don't know this problem, but that's what we also study in the papers. That's one additional model for which we include a certain prediction. And what we do here is we include a prediction for every node. And in this case, the prediction is the maximum edge weight adjacent to some kind of node V. And the main reason why I want to note or to discuss this is that this is an example of a model where we actually don't predict something about some kind of optimal solution, but we just select or we just predict something about the input of the instance. So we only predict something about, okay, for this node B, for example, what is the maximum edge weight that node B is adjacent to, and the prediction that we consider. And we can then obtain similar results as we had for the secretary problem and for this online Vipertite matching problem. So we can get approximation guarantees that are of a similar flavor as the pictures I illustrated before. And with that, I would actually like to conclude this talk. And thank you for attending. And if you have any questions, I would be happy to answer them at this point.
Okay, so if anybody has any question, you can unmute yourself and ask your questions.
I have a question. I was just wondering if there are situations where you actually can get decent predictions. I mean, the problems are kind of abstract, so I'm not sure, but maybe like for the online Vipertite matching, maybe there's like ad advertising or something, and there are data from past advertisement auctions.
Yeah, exactly. Yeah, that's also one of the, definitely. That's also one of the motivating examples. I must say I'm not familiar with if the data that is collected also by companies would be directly implementable in these type of algorithms, but that's definitely one of the motivations as well, where indeed you want to solve some kind of like online auctions where you have the possibility to sell multiple items online. it's a very good point.
Any other question? So I have one question. Did you try, like, when you have these different phases of exploring and exploiting, did you think of like throwing a coin and deciding if you want to, like, instead of having like explicitly one phase of exploration, one phase of exploitation, each arrival, like flip a coin if you want to use that, like use this method versus that method.
Yeah. So that's actually you can also do that, and sometimes you can also get better approximation guarantees. So for us, the focus was really on deterministic algorithms, because sometimes also in these settings, like once you start to allow randomized algorithms, it might become very easy to get improvements, because then indeed you can even do something which is even more rough and just say at the start of your algorithm, you just flip a coin, and with probability a half, you just fully try to exploit the prediction, and with probability a half, you just run the original algorithm. And then in some cases, you also already get improved approximation guarantees. So sometimes deterministically, this is even, it's much easier to achieve. And for that reason, also we focus on deterministic algorithms, where this becomes where you can no longer use these sort of random coin flips to decide if you want to exploit the prediction or if you want to run the classical algorithm. That's at least that's where sort of technically the most interesting problems come up. But it's definitely true that you can also consider algorithms where you randomize over either exploiting the predictions or running a classical algorithm for an online selection problem.
Yeah, one more question. So for the secretary problem, I mean the classic one, knowing how many secretaries you will interview is important, right?
Yes.
But it's not always known, like how many secretaries you would get. Like, do you know any result like that, either with unknown n, or if like they use some machine learning advice to predict n itself?
Yeah. So people have also studied this problem, I think, up and down, when you don't know the total number of secretaries. But now from the top of my head, I don't know what the... sometimes you can also... does it work? Let me think. I'm not sure if you can do anything meaningful when you don't know the total number of secretaries.
You know what would make sense in that case is to actually do this exploitation things with the coin, because at the end, in expectation, if there's a certain probability, you can get, like, let's say in 1/e, you just save it with the rest of the probability you. So I was wondering if anything like that have been done.
Yeah, that might be possible. Yeah, I would have to look this up, because I mean, I know people have studied like these settings where there's an unknown number of secretaries, for example. You could also assume that this number comes from some kind of distribution. That you should still be able to give some meaningful results by means of sampling, I think. But I would not know if our results are directly applicable to those type of settings as well. But it would definitely be interesting.
Okay, so if there are no other questions, let's thank Pieter again. And yeah, thank you.